This is a very brief run through the global carbon cycle. I'm going to use the so-called Princeton primer from David Archer, a good friend from University of Chicago, who just told me some pretty amazing stories about what he's up to. Check him out. All right. This carbon cycle story is really huge. There is a massive amount of literature. Obviously, now it's at the center of climate change and human activities and human impact on climate change. But how do we get a grip on it without going into all sorts of details? So I found this primer to be ideal for a brief introduction. So I'm going to do it, and then it's up to you to follow up on the details that you feel you need for your research or your understanding or whatever, right? We have kind of done it through the courses I've already posted in terms of carbon sequestration and various other drawdown ideas and so on and so forth. So this is from the European Union, which is a carbon cycle perturbation, human perturbation for the year 2019, I think. But I'm going to use it just to make a few points about the various reservoirs we have, like the atmosphere, ocean, land, and then the fluxes between them. So the key concept, of course, is that human beings are burning fossil fuel, which is estimated at a certain reservoir size, and we are digging it up, burning it, and putting a certain amount of carbon flux into the atmosphere, and then that emission we are creating, not just by fossil fuel but deforestation, cement production, steel production, etc., and all that carbon is either accumulating in the atmosphere or getting into various reservoirs. So that's the idea of a global carbon cycle. So just look at some of the numbers here. Okay, so anthropogenic fluxes 2009 to 2018 average gigaton CO2 per year. When you look at carbon cycle, there are all various kinds of units used. Gigaton CO2 and gigaton carbon are the most common. There is a multiplication factor between the two that I will show a little bit later on. And then people also use CO2 equivalent, which converts methane, nitrous oxide, other greenhouse gases into CO2 using the chemistry and so on for that. Okay, so we have land use change, ocean uptake, and atmospheric increase, and there is a budget imbalance when you take all the numbers, because we don't have very accurate measurements. Okay, so coal reserves, for example, here 445 to 540 gigaton carbon. You can use the average annual consumption and see how long that'll last us, but now we know that we don't want to burn it anyways. Oil reserves 175 to 265 gigaton carbon. We would like to leave this asset buried and not use it up. Gas reserves 385 to 1135 gigaton carbon, and then we are putting 9.5 gigaton CO2 with some uncertainty of 9 to 10, and then volcanoes are putting about 0.1, and then permafrost, soils, so those are the reservoirs. All these are reservoirs, which means it's like a tank. How much CO2 is it holding, as opposed to fluxes that are in and out. So you can see here vegetation has a certain reservoir size, and then there is a flux in and a flux out. Rivers and lakes, coasts, and surface sediments in the ocean, oceanic organic carbon, and marine biota, which is a very small part of it. But if you look at dissolved inorganic carbon in the ocean, for example, that's 38,000 gigatons, which compared to these numbers is massive. So ocean obviously is a massive reservoir, and if you look at the sediments, there is another much bigger reservoir as well. Atmosphere obviously is accumulating at plus 4.9 gigaton CO2 during this period over which it is averaged, and the reservoir size of the atmosphere essentially turns out to be twice the ppm that we talk about normally, measured at Mauna Loa and various other places. So when we say 860 gigaton carbon, that's 430, which is what we have done over this period. So other thing you want to note is that you have a net uptake into the ocean here, net uptake into land here, and then there is the imbalance. But when you look at uptake estimates and so on, you have to be careful because it's a small difference between two large numbers. So ocean is taking up 90 gigaton CO2 per year and giving back out about 90. So there is a small difference which amounts to net uptake, which is either a solubility uptake where the atmosphere just puts CO2 into the ocean and that's taken down into deeper ocean where it takes a longer time to come back, or there is photosynthesis by the phytoplankton which take up CO2 and then sink it out to some extent. So there is what is called a solubility pump and a biological pump. So we will look at these details later on as we go forward with the course. Throughout the history of the planet, if you go to the beginning of Earth, there are various estimates with all kinds of uncertainties, with various evidences from stomata, liverworts, paleosols, and so on. So for 100 million years, so it's just about the beginning of the Cambrian, or well into the Cambrian, where the number of species jumped at 540 million years ago or so. And you can see that the numbers have been high compared to today. So we were in the Holocene here, the scale is nonlinear here. Various observations from ice cores, model projections and so on for the future keep us somewhere down here, but we have been as high as 2000 ppm, and during the time of the dinosaurs here at 65 million years ago or so we were at 1000 ppm. We have dropped over 50 million years because of various hypotheses that claim that it's because of the rising of the Himalayas and faster weathering rates, evolution of the monsoons, and so on and so forth. And here is where we are headed based on what kind of emission scenarios we get locked into. Right now we are on the high emission scenarios, but with renewables and various agreements, Paris Agreement, carbon capture and drawdown and so on, we are hoping to stay way below where this would take us. So for keeping our 2.2 degrees centigrade global warming target, or 1.5 degrees C target, with a probability of 50% or 66%, we want to be able to reduce our emissions quite a bit, already starting now, but we are way behind anyways. So throughout the history, CO2 has been a key player, and this is the corresponding temperature anomalies with some base period like 1960 to 1990. Okay, so these are anomalies estimated with various paleo proxies, ice cores, sediments, etc., etc. And going back to the Cambrian, it was 14 degrees C warmer than we are at present down here, and the fastest warming we have seen, like the Paleocene, Eocene thermal maximum, was one of the fastest, but now it's actually much slower than what we are experiencing right now. Of course, here there were no humans, so we cannot say Earth has been warm before, so why bother? Why worry? But we have evolved basically in this fairly benign steady temperature with a range of only about 0.5 to 1 degree change, and we are jumping out of it really at a very fast rate. So we have to worry about what will happen to us. The planet is not going anywhere, and biology will survive. Somehow many species will go extinct, but there will be many species that will survive. So it's the question of our survival. So CO2 is a key player throughout Earth's history, and it is a key element of the Earth's energy balance on various time scales. So we will look at some of those details as we go forward. Okay, so let me stop this podcast here, and I'll add some more preliminaries in the next podcast.